Let us continue our discussion of examples of topologies on R. Already we have discussed it, the usual topology or the standard topology on R, which is induced by the usual Pythagorean metric. Now, another topology we can define on R, which is called as semi-open interval topology. Here, the description of the open sets are as follows. Tau consists of those subsets of R, U. For every x in U, there exists some R positive such that x xr, that is, you can x xr, I mean left closed x plus r, right open, is subset of U. So just take any subset U of R, declare that it is open. For every x inside U, if you are able to find a half open interval closed from left and open at right, starting from x and a positive distance r towards that. If such open intervals, semi-open intervals are available for every x in U, then we say that such a U is open. One can easily check that this tau in fact defines a topology on R, and we will call that it's a semi-open interval topology. This topology is going to be strictly finer than usual topology on R. To prove that, what the only fact you have to use is the following. Take any interval AB. This is always contained in closed A, open at B interval. This containment will say you why it is going to be a strictly finer topology than the usual topology. Now, in a very similar way, one can think about the description in another kind of semi-open interval topology, which can be closed at right and open at left. That's another way of doing that also, which you can try it as an exercise. Now, another topology can be defined, which is very useful. We will call that order topology. Basically, it comes out from the idea that, see, R, if you are looking at, it's an ordered set. Less than or equal to will make a linear order on R. So this order structure actually gives us a topology. To understand what exactly is this topology is, see, we remember the open intervals. Once less than or equal to is the order there, and for any A and B real numbers, A, B, the open bounded interval is known for us. So this ABs will generate us a nice collection of topologies, nice collection of open sets. So here, a subset of R is said to be open or declared to be open if for every x in U, what you are aiming at is if there exists an open bounded interval AB which take care of your x and which is sitting inside U. In such a situation, U is declared to be open. So this openness we are declaring using the order structure of R. We can verify that it is indeed a topology, and we call that it is an order topology on R. But a moment's thought will give that this order topology is going to be the same as that of the usual or standard topology. We know that standard topology, the metric topology, actually the topology is induced from the Euclidean metric, and we know that BXRs, the open ball centered at x and some positive radius, are going to be giving the ingredients for the metric topology or usual topology on R. But you can just look at, see, any open bounded interval AB, one can view it as an open ball centered at A plus B by 2, and whose radius can be considered as the B minus A by 2. So you can just look back also. So any open ball is obviously can be thought of an open bounded interval. which is centered at x, and the endpoints are x minus r and x plus r. So this transition or swapping allows us to say easily that order topology coincides with metric topology or the usual topology on R. It's a very useful fact. In analysis, we have seen that, in fact, these bounded open intervals are enough to understand all open sets in R. Now, one can just look at this real line once again. It's a metric space with the usual metric. So the usual topology on R, they are coming from the balls, as we have mentioned, that balls centered at a point x and R is known for us. So our definition for an open set here, U is said to be open if for every x in U, if you are able to find a ball centered at and with some positive radius R. This R is depending on your x. This is what the definition for an open set in R. One can easily see that this implies the singleton X is going to be contained in Bxr, which is a subset of U. So it in turn gives, you just take all the unions of all these singletons, X is working inside U, is again going to be subset of all these kind of Bxrs, where X is playing inside U's. And obviously union of these fellows are again U, stable. So the left hand side, this again makes U, which says that, which will give the idea that U can be written as the union of all these Bxrs, which says that any open set U can be written as the union of these open balls. It is not this whatever we work through is not only for, not the only solution it gives for R. Any metric space this will work. You take any metric space XD, it induces a topology. You will get a topology out of that. If U is open with respect to that too, the same methodology will work, which says that any open set U in X, which is available in 2, can be written as the union of open balls. So open balls are giving you the idea how to manufacture all open sets. In analysis course, we have seen this. In the real analysis, we have seen that any open set can be written as the union of bounded open intervals. We have in just before we have seen that all bounded open intervals are basically the open balls. So we can very formally define this concept. Start with any topological space X2. You just look at a subfamily B of 2. We are going to call that B as a base for our 2 if every member of these 2 can be expressed as some unions of members of B. So this is what we have to consider. And we have already considered in the metric spaces, as I just mentioned. If a metric space is given, it induces the metric topology. Open sets are described with respect to this metric. And ball, if you are just considering the subcollection B of all balls, I mean Bxr, X is working inside X and R is any positive real number, then one moment's thought or our discussion will justify that this B is indeed a topology 2. It induces the topology 2, the metric topology 2 on X. So how we will move that? So B is a subcollection. All the balls are indeed open sets, and that balls are enough to generate all general open sets. You take any open set, that open set can be written as the union of members from here, which says that the track is like that. From the subcollection to the full open sets, if you want to move, just try all possible or possibilities of taking unions from here. Definitely will give all open sets from here. Whatever be the open sets are supplied from here. So that is one aspect of understanding the whole open set to a subfamily which itself will give without sacrifice all the open sets by just looking at arbitrary or possible unions from them. It will give the idea for that. Remember that in the definition of topology or the open sets whenever you discussed, except the first axiom, empty set as well as the whole set is inside 2. We are taking arbitrary unions closeness as well as finite intersection closeness. So if you are just relaxing the second one, then you'll be reaching at the stage of a base. A base for a topology is like that. You just take open subcollections of two, but from which you can manufacture all open sets by just taking arbitrary unions from out of each. So we are not sacrificing much, we will get it back. So this will be a good tool to understand the whole open sets by looking at a smaller family. Obviously, all topologies are once you are given with a topology, that itself can be taken as taken as a base also.